Alright, in this video we're going to talk about the basics of nuclear fusion and nuclear fission. They're kind of opposites. We're going to spend a lot more time talking about fission than fusion, but we're going to talk about fusion first. So, nuclear fusion. The basic concept here is that you have light elements that are being smashed together and they form heavier elements, and in the process some of the mass gets converted to energy. So let me write that out. So light elements, usually things like hydrogen and helium, really lightweight elements, combine to form heavier elements. And the mass, some of the mass is converted to energy. And I'm talking like ridiculous amounts of energy. So this is pretty much the type of reaction that's occurring like in the sun and like hydrogen bombs. The reason they're called hydrogen bombs is they're literally taking hydrogens and smashing them together. Okay. The sun, let's talk about that one. Most stars are pretty much made of hydrogen. Hydrogen is the most common element in the universe. It is literally just a proton and an electron. If these things are able to smash together and can form some neutrons, and the neutrons start adding to the mass, this is the most common type of reaction. It's basically hydrogen 2 and hydrogen 3. These are not the most common isotopes. The most common isotope is hydrogen 1. Okay, this one actually has a special name, which is deuterium, and this one has a special name called tritium. I don't know why I capitalized that and not that one, but it doesn't really matter. Okay, well what happens is, if you have really high temperatures and really high pressures, what happens is these things squish together and we stop worrying about what element it is and we worry about how many protons and neutrons there are. And so what happens is these two masses add together and you end up forming a helium. And the most stable form of helium is helium-2. This is an alpha particle. And then we lose a neutron in there, or we get a neutron in there also. Okay, which helps go to form masses, or add to the mass of H1 or H2 to form these other things to help the process keep going. The important part is we get tons and tons of energy. Okay, so the reason nuclear power tends to not use fusion as an option is the temperatures required for this. I don't remember the exact number. I want to say it's like 43,000 degrees Kelvin, some stupid high number that would basically melt any material that we could have. These type of temperatures only really occur, like, I don't know, in stars. But honestly, this is what's powering like solar power. So people are like, yeah, I want to use nuclear fusion for powering my house. This is not a realistic option in terms of blowing these things up. But getting a solar power or a solar panel on the top of your house and absorbing the energy coming out of the sun that's already doing this, kind of the easiest answer. Obviously, we know how to make hydrogen bombs, but they're not like stable. We don't know how to continually get nuclear fusion to occur in a way that we can harness it for energy in a safe manner. Okay. All right, so it is important. It is literally the reason life is on this planet, but it's not useful from a like lab perspective because the temperatures required are so hot that it literally destroys any matter in the area. The other option that we are going to focus on is nuclear fission. Oops. So fission is kind of the opposite of fusion, sort of. It's when heavy elements, usually things like uranium or things on the bottom of the periodic table, things that are really heavy. Heavy elements are split into lighter elements, and any mass conversion in there gets converted to energy also. So either way, mass is converted to energy. Okay, so this one is pretty common as far as nuclear power sources. So like nuclear power plants, this is what they do. So for example, let's kind of talk through this one, I guess. If you had a power plant, what you have is typically, most power plants use uranium-235. It's an unstable enough isotope that it can undergo nuclear fission pretty readily. And what you do is you take a uranium-235, that's supposed to say 235, sorry, and you shoot a neutron at it. There are really specific conditions, and it's, not just as easy as like throwing it across the room. And then what happens is this breaks down into two lighter weight elements, okay? It's going to be kind of random which two elements they make, but this is element 92. I would say whatever they combine into, they're going to be two things that add up to 92. So if it broke into like calcium, which is element 20, it should probably also break into like a hafnium. If one of the elements it broke into is like zinc, well, then it's going to need to be 62, whatever that comes out to. Samarium. But it's kind of random. But the important part is it breaks into two elements, but it also tends to release a couple more neutrons. I'm just going to write them as N's from here on out. And as long as you have enough uranium atoms around, I'm going to stop writing the 235, it'll continually do this. And as long as you just keep having uraniums around, this will go on forever. And it'll release a ridiculous amount of energy every single time one of these happens. But this process is called a chain reaction. Okay? So, this is what powers nuclear power plants. Let's kind of talk about the energy component of this one. So, it turns out for uranium-235 fission, it turns out that you get 8 times 10 to the 7th kilojoules per gram of uranium. Okay? And at first glance, you're like, I don't know, is that a lot? This is about the equivalent of burning 3 tons of coal. Okay, so every gram of uranium releases the same amount of energy as 3 tons of coal being burned. Okay, this is a ridiculous amount of energy. Okay, so the way this process works kind of implies that you can't just have like one uranium atom. I mean, yes, you get energy out of that, but yeah, like, I guess let's add this on here. So one of the other things you get is energy. And so on and so forth. You get energy in the form of radiation or light or whatever, heat, whatever form it comes out in. Okay, but the idea is every single one of these releases more energy, and the idea is that it piles up. So, in order for this to work, you have to have a minimum amount of have to have a minimum amount of uranium around for the chain reaction to occur. Okay, and this is something called a critical mass. So this is the smallest amount of uranium-235, or whatever element you're undergoing fission with. Uranium-235 is the kind of go-to standard answer. This is the smallest amount needed to sustain a chain reaction. I can't give you like a specific number, partly because I don't know it, but I also know it depends on the purity of the uranium. If you have impurities in there, you need more mass to make up the difference. It also depends on the configuration. If you have it in a ball, you need a different amount than if you have it in like rods, or if you have it in squares. The shape matters a lot too. But the idea is, if you have something below this critical mass, okay, whatever the mass and shape is, this reaction it'll be a chain reaction for a while, but eventually these neutrons will shoot out and hit something besides the uranium, and the reaction will die. Okay, so if you want this reaction to be continuous and self-sustaining, you're going to have to be above that critical mass. But if you're above critical mass, it's hard to stop the energy. Okay, so in the next video, we're going to talk about how nuclear power plants work, and we'll see how they deal with this critical mass thing. All right, thanks.